And Eric Somers. I will talk about the minimal singularities in nilpotent orbits and a conjecture of Lusztig. So first of all, I will introduce some basic notions on nilpotent orbits and also some geometry on nilpotent orbits. Then I will go to talk about the minimal singularities, and the last part will be concerned in the conjecture of Lusztig. So let me start with G. It's just a complex and simple Lie algebra. So you can just think of SLN. And the capital G is the adjoint Lie group of G. So this means the center. The adjoint means the center is just trivial. So you just take any Lie group with the Lie algebra G, then you quotient by the center. You obtain the adjoint group. So in the case of SLN, so what you get is just PSLN. So take a nilpotent element. So for example, in this case, SLN case, so what you take is just a nilpotent matrix. So you take a non-zero nilpotent matrix. Then this capital G, this acts on G on this Lie algebra just by adjoint action. So in this case, you get a nilpotent orbit. For example, in the case of SLN, what you get is just conjugacy classes. So just G is SLN. So nilpotent orbits are just conjugacy classes of nilpotent matrix. So from this way, you can say it's very easy, it's very elementary. However, since this is the orbit, so you obtain a smooth manifold. In fact, it enjoys many special properties. For example, first of all, this is a smooth holomorphic symplectic manifold. Means you have a holomorphic symplectic structure. This is what we call the Costan-Kirchhoff-Suchio form. And also, this is stable under the dilation action of C star. Furthermore, under this action, you have this prop. So this means just as in Karadin's talk. So L is just 1. So this is a very simple example. And also, if you take the closure is always singular, except when x is 0. So this is just 1 point. Otherwise, it will be singular. And also, it's a union of finitely many nilpotent orbits. So from the first point, you say the dimension of all x, this orbit is even dimensional. So this is a union of finitely many even dimensional symmetrical variety. So what you get is this closure is normal in codimension 1. But in general, it's not normal. And also, nilpotent orbits are classified by weighted Dingin diagrams and by partitions in the case of classic types. For example, in the case of SLN, so conjugacy classes, so in each classes, so you can always find just the Jordan form, JD1 and JDK. So JDI is just the matrix like this. And such that the sum of DI is just N. So this is a one-to-one correspondence. Means in the case of SLN, nilpotent orbits are just parameterized by partitions of N. And in other cases, it's similar, but given by some special partitions of N. So in general, O bar is not normal, except for the case of type A. In this case, this is shown by Kraft and Porchesi. Then every closure in SLN are just normal. Now I take the OTID, the normalization of this orbit. So on the smooth part, you have a holomorphic symmetric form. And what has been shown by Panshev and Hinich, they showed that for any resolution, this form, so you have this form is just defined on the open part, on the O. So the pole bank is defined just on an open part of Z. But what they have shown is that this lifted form on the open part can be always extended to a form on Z. So in other words, this shows that the normalization is just a symplectic singularity, just an example of symplectic singularity. And in general, the extended two form is not non-degenerated. But in the case of non-degenerated, then we get a symplectic resolution, just in the previous talk. However, in general, the normalization does not admit any creeping resolution. So in this case, creeping resolution means it's just a symplectic resolution. Means the extended two form is gives a symplectic two form on Z. So however, it always admits a Q factorial terminalization. So Q factorial terminalization is somehow weaker than creeping resolution. It's just a bidirectional map. So this is a bidirectional map. Such that we have two conditions. First of all, is that this one, X, has Q factorial terminal singularity. So for creeping resolution, this is just smooth. So it always satisfies this condition. And secondly, pi is creepant, means pi of KO tiered is just K of X, is just trivial. So this is the Q factorial terminalization. So for creeping resolution, what we replace just X is smooth. And in general, a Q factorial termination exists always. But however, in our situation, this becomes much simple because in this case, all Q factorial terminations are of a very special simple form. So in fact, we can find all Q factorial terminalizations. We can determine all X such that this gives a Q factorial termination. To introduce this simple form, I will give some notation. So let me start with Q, just a parabolic subgroup. And the small q is just the Levy decomposition of Q. So for example, in the case of SN, so this is very simple. You can just consider these all of these in terms of matrix. So Q, a subgroup of G, is just SLN, say PSLN, and then parabolic. Parabolic means the quotient is a projective variety, and in this case you can just think about something like this: the matrix of some form. Just something like this. So these are non-zero. Non-zero terms can only be on this part, and these are zero terms. Matrix like this, and when you take so this is a small q. This is the Lie algebra of this parabolic subgroup. And when you decompose, so this is just something like this. So just take the diagonal part. So this is the reductive part. This is LQ, and plus some nilpotent part. So this is just something like this. So this is NQ. So this is the decomposition of the Levy decomposition. And now what I take is just a nilpotent orbit in this reductive part. Means I take a nilpotent orbit in this one. But the nilpotent, the orbit is with respect to the action of this Lie group, LQ. So not with respect to the action of G. So it's just a small orbit inside each term. So fix such a nilpotent orbit, then I can consider the action of G on this one. So this is just a nilpotent orbit for the small action, for the small group, LQ, not for the whole group. So when you act on this, in general, a priori, this is not a nilpotent orbit closure. But however, in this case, this can be shown by Lusztig and Spartenstein. This is always a nilpotent orbit closure, O bar. So from this, you can form the following map. So from G times P and Q. Then you take just the NQ plus OT bar from this map to just the closure. Just the closure of G, the action of this one plus OT bar, and this is just the O bar. So from this you get a geometrically finite map. And in general, this is not bidirectional. In this case, we call this orbit is called an induced orbit. And if this orbit cannot come from this form, then this will be called rigid. We have always the classification of rigid orbit and also induced orbit. And this map will be called the generalized Springer map. What we call the generalized, this is because if you just consider OT just 0, so when OT is just 0, so maybe I did upstairs. So OT equals to 0. In this case, this map, this is just the G times Q and NQ. So this is just the coordinate space of G over Q and to the nilpotent orbit. So this is a usual Springer map. In general, this is just finite, geometrically finite. It's not always bidirectional. And now the theorem showed by Namigawa for the case of G classical, and by myself for the case of equational case, is the following. If you fix any simple complex Lie algebra G, and O is just a nilpotent orbit, then any Q factorial terminalization of O bar is given. There are two ways. The first is just you take the normalization of this closure. So sometimes you get a Q factorial terminal singularities. So you get the Q factorial terminalization. And the other way is just take a normalization of a generalized Springer map. So you just take some generalized Springer. In particular, this will require this map is bidirectional, and also the normalization. This is equivalent, and also in particular, this shows that O is an induced orbit. So to match it, the normalization always gives a Q factorial terminalization. But also there are some induced orbit whose normalization is the Q factorial terminal. And also the geometry of these blocks of these terminalizations are studied just by connected by Mukai blocks. So as just I said, so when this is bidirectional, then we get a Springer resolution. So this is just the geometry of this orbit.
Yeah. What OT here in the levy? Is it rigid there, or is it also?
Yeah, you can always take it rigid. Yeah. In fact, in most cases, this is orbit in classic type. And now I talk about the minimal singularities. So in nilpotent orbits, there are, as I said before, O bar is the union of nilpotent orbits. So O bar is the union of small orbit, OI. So you can draw a diagram like this. So you start from O. So you consider all the OIs. So you have a diagram like this: O1, it could be O2, O3, and so on, like this. The property is that OI, this closure is contained in this one. Or for example, this line means O1, the closure O1 is contained in the closure of the former one. For example, this implies O3 is contained in O1 bar. So this is a diagram, what we call the Hess diagram. So from this, so you have minimal digitalizations. Means this is the minimal digitalization, and this is the minimal digitalization of this orbit to this orbit. And what we would like to study is the minimal singularities of this variety along this along this minimal digitalization. Means minimal singularities are just the geometric singularities of the closure. Minimal singularities is just the geometric singularities, minimal singularities of bar. What this is definition is just the geometric singularities. Singularities of O. So means I just consider the biggest orbit contained in the closure, in the singular part, and I consider the singularity along this orbit, but not the small one. This means you just take for example, I take a little, if I write down is just I take a minimal digitalization, means this O prime bar is an irreducible component of this of the singular locus. So you get something like this. So O prime. So this is just O prime in your notation. And then you take a transverse slice inside O. So this is a big O bar. Inside this you take a transverse slice to this orbit. Then what you get is you can take a slowed wave transverse slice or any other you like. So this is a singularity. This you get a singular. This you get a variety which is singular only at this point. So you get an isolated singularity. And furthermore, this singularity has a dimension is just the codimension of this orbit inside the whole space. And the normalization gives an isolated symplectic singularity. So this makes sense to for one to study the minimal singularities of nilpotent orbit closure, because this gives some interesting examples of isolated symplectic singularity. In general, it's very difficult to construct new examples of symplectic singularities. And we hope for isolated symplectic singularities, maybe there are not much. So for this problem, in fact, this has been studied much before. The first case is a subregular case. So this is due to Grothendieck and Briscoe, slowed wave, and A-low, and so on. So in fact, what they have studied is the nilpotent cone. So for the nilpotent cone, so this is union of all nilpotent elements. So nilpotent cone. So this is all nilpotent elements. In G. So for this, we have, in fact, this is a closure of a nilpotent orbit. This is just the biggest one, and then you have the subregular case. So the subregular. In fact, we can show that the n minus O is just the O bar of subregular. And in fact, this is has a codimension 2. So this is codimension 2. So when you take this singular transverse, so you get so this singular transverse of this normal cone along this subregular. So you get a surface singularity. Furthermore, this surface singularity is symplectic singularity. So is a surface singularity of RDP, rational double points. So it can be ADE type. And in fact, what they have proved is that if G is sampling list, for example, ADE type, in this case, the singularity of this transverse slice is just the same type as G. And for other type is just the folding. For example, the CN case is just given by the folding. You just take this one, and the E6, for example, E6 is either to F4. You just take something like this. You just collapse this one. Just take the folding. folding of this one to this F4. So E6 F4 is gives the singularity of E6 and so on. And then later on, Kraft and Porchesi in 82 studied the classic types. For classic types, in fact, they do not find many examples of new examples of this isolated symplectic singularities. In fact, what they find, for example, in dimension 2, we just find rational dot points of type AK or D, type A or D, because we are in classic types. So in this case, these are normal case, means the closure is normal. And also of type AK union AK, this means the singularity is just intersect transversely at the singular point. For example, A1 type. This is something like this. So this is A1 type. So A1 union with A1 is something like this. So this is singularity of this one. And in this case, this is a non-normal case, means the closure of the orbit is not normal, and only in this case. So in dimension 2, they just find AD and also this particular form. And when dimension is bigger than 2, what is found is just the O-mean bar. O-mean is just the smallest non-zero orbit, smallest non-zero nilpotent orbit. So if you take the closure, so this is just the O-mean union, just 1 point. So this is also an isolated symplectic singularity. So in codomain bigger than 1, they just find this. So this is
again of type A or B?
no, any type, because the O-mean exists for any type.
Yes, but which ones show up here?
Yeah, for any type.
So you find E6 even?
No, E6, no, you cannot find it. Yeah, A, B, C, D. Yeah, classic type.
Can you have something like C2, which is pinched? I mean, geometrically it's...
No, you mean this one or this one?
Dimension 2, I think.
Yeah, dimension 2, no, C2, no. They just get AK union AK. There's a low. Yeah.
So this is a statement about codimension of the singular locus.
Which is?
This theory.
Yeah, dimension.
No, yeah. The dimension is a codimension. Is a codimension of the yeah.
So the result is about this codimension.
No. For example, for this case, a priori it can be other isolated singularities. For this case, yeah, Schoen's normalization is just AD type, but the configuration can be. And then Kraft studied the type of G2. So for this case, this is so let me just give you some examples of how the geometry can be used to determine the minimal singularities. So for G2 case, so the argument I will use is different from the paper of Kraft. In fact, he used some embedding of G2 into SO7. Then he used the results of SO7. But I will use some geometry of the resolutions. So for G2, we have the orbit closures like this. So if I draw the diagram, so G2, then this is G2 A1. This is A1 shared, and this is A1, and this is 0. So this is dimension 12. This is 10. This is 8, 6, 0. So so we know this singularity of this diagram. So this is just a D3, D4. So this is just a D4. You just map the connect to this to G2, and for this we know also this is O-mean. O-mean in G2, so this is just divided by small g, G2. And what we should determine is just this digitalization and also this digitalization. So for this one, this is easy for this one. So for this one, in fact, what we can show is that this is an even orbit. So in fact, this admits a symplectic resolution like this: G over P to O bar. Just that the G2 of A1. So we have a symplectic resolution. In fact, the P is parabolic P is maximal, because in G2 you do not have many parabolics, so it's maximal. In particular, this would imply the B2 of this is just 1. So the exceptional set of this one, this is just the irreducible divisor, and so you map to something like this, to A1 tiered closure. And since this is reducible, and also this gives a symplectic resolution, so this you just count how many P1s appear in this. And also this is symplectically connected, so this is just one P1. So geometrically, this is just a P1 fibrilation. So geometrically. So this means the singularity of this is just A1 type. So you do not have choice. And for the other one, still we can use similar. Oh no, sorry. So for the other one, we can use some similar argument, but in this case, the situation is different because this does not have any symplectic resolution. But what we can have is just Jacobson-Mohorovec resolutions, something like this, still a vector bound over flank variety. And in this case, P is still maximal. So the exceptional set is still irreducible divisor because O bar is the Q factorial. So this gives the Kx is just A times E for some A bigger or 0. But the case we should rule out is A is 0. This is because A tiered does not have any symplectic resolution. So A is strictly bigger. This means the O tiered has terminal singularities. This would imply that the codimension is bigger than 4. But means the normalization of this codimension has singular part in only codimension at least 4, but this has codimension 2. So means the singularity of this one is smooth. So this is the surface singularity, but whose normalization is smooth.
So this is the pinched section. This is the pinched section, which
Okay. Whose normalization is smooth. So this singularity, we will denote this by M. In fact, for this singularity, we can study furthermore. We can show this. This singularity is asymptotic to the image of this one. So the first part is just A1 singularity, but we should add the other 4 terms. So we have 3 methods to prove this, but before no one has made out in Kraft's paper. He just studied seeing that the normalization is smooth, but no one has written out this explicitly. So in general, the same methods holds for codimension 2 case essentially. So for codimension 2 case, so if this O tiered has only terminal singularities, then the situation is somehow similar to this one. The normalization is smooth. So otherwise, by the theorem in the first section, so we can find a Q factorial terminalization like this of this form. From this, so we get a minimal resolution of the surface singularities. What we need to compute is the P1s, how many P1s contained in the fiber, and also the monotropic action of the base on the fibers. So to compute the P1 overall point, P1 contained in the fiber, we have the following formula. Yeah, it's quite complicated, but this comes from substringal representations and substringal correspondence, and also some formula from Baohua McPherson. From this, technically we can compute the number of P1s contained in the minimal resolution. And from this, so we can also compute the number of irreducible divisors in the exceptional set, just by argument for the Betti numbers. And from this, so you can compare the two to get some information on the types of the singularities. So there are some types, for example, like this. Still, this is not enough to determine all the types. For example, there are some types, for example, D4 and A4, sometimes it's difficult to distinguish. Because when they all have two irreducible components and also 4 P1s over the fiber. In this case, we need to do some intersection, compute the intersections of these P1s using some representation theory. And also this also get the monotomic action on the singularity, because if you have an and for example this you have the action of S2, and this you have action of S2, and this is S3, and so on. So in most cases in higher codimension, we can use the following proposition. It's just saying that you can take a small subgroup. If the codimension match, then and also this is the unibranch, then the singularity does not change. So in most cases we can use this. Just taking H is just the reductive part of the stabilizer of a point, and in this case we can obtain. So let me just show you the results that we obtained. So to show the results, we just introduce some notations for the singularities. So dimension 2 case. So we have this one AN, DN, EN, AD type surface singularities. And also we have some angular singularities like this A2N minus 1 with S2 action. So the S2 action is just the monotomic action. So we get the record of the monotomic action. And also DN with S2, and also D4 with S3, and so on. E6 with this will denoted by F4, and this is BCG. And also the minimal singularity of G2 is just denoted by M. And for codimension bigger than dimension is at least 4, so we have also A, B, C, D, E, G, E, F. So this is just the OMIM. This denotes the OMIM in the corresponding Lie algebra. And also we still have some actions of the component group. So we have DN with S2 and D4 with S3 and so on. This with AN plus. So what we obtain, the results, I just show you the diagrams. So it's something like this. So this is type F4. So we get some results on this digitalization. And also E6. So you look at the E6, so there are something we do not know. And also E7. E7 there are also a few, and also E8. Okay, so you cannot see much information from this. So this is why we can see something interesting if we just not take all the nilpotent orbits inside, but we just take some special nilpotent orbits. In this way, we can see some duality between the singularities. And the special nilpotent orbits, it comes from the Springer correspondence. So which says the Springer correspondence says that if you take W is a wet group, and you can associate to any W irreducible modules to a nilpotent orbit together with an irreducible representation of the component group. But this is not surjective. However, this is just an injective morphism, an injective map. And a nilpotent orbit is called special. So this definition due to Lusztig. If the irreducible representation of this, you take the phi is just the trivial representation of this component group. So this is a special W representation. So I do not tell you what the special W representation means, but we just know, we will see, for examples, we know all the classifications of special nilpotent orbits. And also, these special nilpotent orbits are very important in representation theory. For example, in the classification of irreducible complex representation of a reductive group over a flat field. So this is due to Lusztig. And also classification of primitive ideas in the enveloping algebra of semi-simple real. Yeah, this is the monotomic. This is Springer. Basically, you take the highest cohomology, the top cohomology of the fibers, and upstairs, downstairs you have the action of the pi 1 of the fundamental group. And then
So if they start with a W, how do I get to
this is non-trivial. This is Springer. In fact, what you do is take the.
Like, is there a map going from the left or from the right, or it just happen to?
No.
Have some kind of a lot of representations of and why not? Because there is in the fibers.
You take the fibers, then, for example, you take the orbit. You take the orbit in the nilpotent cone, you take just an element. So you have here you have the Springer fiber. So I've just denoted by B of X. So this has many components. In fact, it has in E6, in E8 it can have thousands of irreducible components. And then you take the cohomology of this top. Over C or over Q. And from this, in fact, we can show that this has the action of W. The wet group acts on this. And also it has also the action of the monotomy coming from the fundamental group of this one. And so from this you can decompose this in terms of this and also in terms of this. And this is how it comes from. Okay, so we have the nilpotent special nilpotent orbits. For example, for the classic types, we know how to determine whether a nilpotent orbit is special or not. In type A, every nilpotent orbit is special. In type B and C, this is special if and only if the transpose partition still defines a nilpotent orbit in G. But in type D is very special. Type D is this is special if and only if the transpose partition defines a nilpotent orbit in Cn, not in D. And the duality is just given by the map, by the transpose map of in the case of type ABC. Other types it's more complicated. So for example, maybe I should go on with the singularities. So what we remarked is that if you take just the connection of special nilpotent orbits, in fact you remove other orbits. You just draw the diagram of the Hess diagrams of special nilpotent orbits. For example, in this case, this is special, this is special, and this is special. This is not special, this is special. So if you draw the diagram, it just becomes simple. G2 and G2A1 and A1. And also this is just 0. So this is just the connection of special nilpotent orbits. And in this case, so this is G2, and this is D4, and this is A1. So this is G2 special. Means this is the minimal special nilpotent orbit. And in this case, we see some duality between this and this, because D4, this is D4 with the action of S3. So in fact, so this goes to G2 SP. So this is duality, how the duality works. So in fact, we observed two facts. First is that so I take a minimal digitalization, then we have the duality map to this, and one of this is of codimension 2. So one of this will give you a surface singularity. And for the surface singularity, in most cases, so we should add some conditions. In most cases, the singularities are exchanged. Means the capital one becomes the smaller one. just like an to an and bn to cn. This is because we should go to the Lagrange dual group. So the Lagrange dual group of bn is just cn. So this situation and this. And also we should there are some exceptions like this. Just the.
What's Lusztig's coming conclusions?
You
didn't say.
Oh yeah. I do not say. Yeah, it's very technical to define this one. Yeah. Most cases, this is just isomorphism, and just for a few cases. In fact, most of this is just one. There are some not many exceptions, and in exceptional cases, most of them are just isomorphism, except a few orbits. So most of them, this is just a trivial. And for this, we have the diagram. If we just pick out the special one, so for F4, you say something like this: F4 is correspond to F4, but this does not correspond to this one. This is because basically we make a star because the canonical quotient it has kernel. This makes the duality does not work, but the others works well. Like this and this. For this we do not know this, like this. And also for E6 and E7 and E8. Also we have many diagrams. So now let me come to the conjecture of Lusztig. In fact, when Lusztig introduced the special nilpotent orbits, he introduced just by the excitation theory. There's no geometry behind his definitions. In fact, till now there's no geometric definitions of special nilpotent orbits. And so in his paper he wrote that special nilpotent orbits are rather mysterious objects and somehow ungeometric. And we feel the need to unveil some of the purely geometric properties of special nilpotent orbits. So to this purpose, in fact, we will define special piece. Special piece means you take just partitions given by special orbits. So means you take the union of all. So for example, if you for this case, so the special piece is like this. This is a special piece. Means take this one. This is a special piece. Means you take the union of all non-spatial orbits contained in the closure, but not the smallest one. For example, means you take this diagram like this. For example, if this is special and this is special, then the special piece consists of this. This is a special piece. Means just the pieces between two special orbits. This is special piece.
Stratification.
This gives a stratification of one of the normal space. And the Lusztig conjecture is in 81. Then every special piece is rationally smooth. So rationally smooth is cohomologically it's just a smooth variety. It behaves like a smooth variety. And this conjecture has been proved by Kraft and Porchesi for classic types, because they can realize.
Not just smooth variety, but they should something like a fine space, right?
Yeah, it looks like a fine space, and also sometimes quotient by a finite group or something like this. Yeah, and also by Benyon and Spatista and Shoji and Lusztig. In fact, all the proofs are not, especially for the exceptional case, the proofs are really technical. They use some tables to check some sense, to check really this. It's not geometric. So for this purpose, in fact, Lusztig conjectured in 1907. So he has conjectured that to explain the rationally smoothness. He conjectured that every special piece is a finite quotient of smooth variety, and also each orbit in this special piece corresponds just to the sets of the image of points whose stabilizers are just in the same conjugacy class of H. Means nilpotent orbits in the special piece just correspond to the conjugacy classes inside this finite group. And for this conjecture, this can be known for classical Lie algebras by Kraft and Porchese. So they used some elementary constructions. They constructed P and H. And for exceptional case, Lusztig in the same paper, he has predicted the group H and also the correspondence between the conjugacy classes in H and also the orbits contained in the special piece. And recently, Acha and Sage, I don't know how to pronounce. So last year they used the Denis Bezout-Kannikov series of perfect coherent shifts to construct a candidate of this one. But in the construction, the P is just normal, rationally smooth. And the P is very complicated. It's just a spectrum of some algebra. So still they cannot prove anything of this. They just propose this should be the right way. So what they need to show is that P is smooth and also the correspondence.
Is the special piece of normal like this?
A priori no, but finally they can prove for exceptional case it's okay. Yeah, this is settled. So our viewpoint is different. So what we did in our paper is that we do not consider the special piece itself, but what we consider is just the transverse slice instead of a special piece. So if you take so this is a special piece. So you take a transverse slice. So like this, take a transverse slice. So locally the piece will just say S. The piece will just looks like O mean. So this is just the minimal orbit inside the special piece. So this is looks like this. And this is smooth one. So what we really concerned is just the transverse slice to the smallest one. Our conjecture is that if you take this one, then things become very simple. So here I take S is just a transverse slice, and S I assume dimension of S is bigger than 4, because in two-dimensional it's just AD type. In this case, in fact, we conjecture this is isomorphic to this quotient. And what we get is just type 2, 3, 4. There's no other one. And so this is uniquely determined by the dimension of S, equivalent to this one. And so the action, so this is Hn is just a Cardan subalgebra, and Sn, this is just a symmetrical group which acts on this by Y group action. So in fact, for this we have a really very simple symplectic resolution of this one, of this quotient. So for this quotient, you have the Hilbert scheme of points of n plus n plus 1 of C2 to symmetrical product of n plus 1 of C2. And now this is just C2 times something times this singularity Hn plus Hn dual quotient by sigma n plus 1. And what we obtain is just from this, so you get a symmetric resolution of this one. And what we predict is also the O bar admits always a symmetric resolution, substringal resolution. When you restrict to this transverse slice, then you get the usual Hilbert resolution. We need to point out that this conjecture does not work for classic types. So this works only for exceptional case. So this is quite, and also this is really a very simple formula. And for this, what we can show is just there are just two cases we cannot show this one. One in F4 and the other in E8. So in F4, the situation like this. So this blank one means the orbits are in the special piece. So this is a special piece. And so there are two. You can cut from this, take a transverse slice from this one, then you get this one. This is just the G2. This corresponds to n equals 2. This we can show. And but if you cut from this transverse slice from this one, then this you get a 6-dimensional case. What we expect is that this should correspond to the n equals to 3. For this case, this is a conjugate class of stabilizers. This coincides with perfectly with this case. And in G8 case, this is more complicated. So the only piece we do not know is this one, the biggest one. So this is the 8-dimensional case. And surely the only way we can say to show this one is just maybe to try to work out the slowed wave transverse slice, compare the equations. But otherwise, I do not know how to show this. So we know the way, but to compute this is really complicated. So this is, in fact, this simulation, this one, this is not the first time which appear. Means the quotient case with the nilpotent orbit case, this is not the first one. In fact, several years ago, I showed that if you take a transverse slice in this orbit, in SP6, then the transverse slice is, in fact, is isomorphic to this product. And also the Springer resolution of this one, when you restrict to the transverse slice, then you get the two Hilbert-Chow resolutions, which are connected by a Mukai flop. So in fact, these have two Springer resolutions, which gives two. But these has just one Springer resolution, one symplectic resolution. And in this case, every orbit like this has only one symplectic resolution. So that's all. Okay, thank you.